Hey, welcome to the Lex channel. So anytime if anyone binge watches some episodes, especially episodes on network protocol development series, as you can see here, once in a while they send me a mail asking me if I can shoot a sample implementation or teach me more specific on a data structure basis on a sample implementation. So they generally want a complete parser design and as well as a protocol design, a custom protocol design and stuff like that. So this is something I often teach my students many times. Once they join the classes, initially their question is they just want to dive deep and they want to get that experience of doing or designing their own protocol as well as doing some sample parser implementation, besides just going through various existing data structures, whether it is in the kernel space or user space, whatever it is. So before in case if you are very new to network software development, I highly recommend you to go through this video series. You should understand one thing, these are taken over a span of long duration. I was completely looking different. In fact, I was talking completely different at that point of time versus the video episodes what you see on the recent days. And so the episodes are quite detailed. As you progress one episode after another episode, you can see here it gets deeper and deeper, and I have discussed various aspects, but some of the things are more theoretical aspects with live demos and stuff like that. But in this episode I want to especially focus on a real working live demo so that you get that full context of how you can start designing and as well as doing your own custom network protocol. And after doing this demo or after watching this and doing it yourself, you can then later go back and then you can explore any existing protocol network stack, whether it is in user space like HTTP or DNS or any such protocol network stack, or in the kernel space like V4 UDP TCP data structure. So this is also something which I have covered in various episodes. You can go here and you can explore. You can see here you have this net device data structure, you have this UDP, and then you have this TCP Ipv4 or IP header data structure. So these are videos I shot really when I started this channel, so it may not be that comfortable to watch because the way I set the camera and the way I was even shooting the entire content. So what I did is I did these two slides so that when I start explaining the code, you get that full context and understanding, and it makes a lot more things easier. So this is one slide, and other than that, this is one slide. So I highly recommend, there is a specific episode in this series I shot. Let me take you guys here. So this is an episode I highly recommend. There are some couple of episodes I shot about fixed header protocols and dynamic header or TLV based protocols, because anytime if you have any user space protocols like DNS or HTTP, these may have or these protocols may have dynamic headers, versus if you think about V4 header or UDP or TCP headers, these are fairly static sized or fixed header sized protocols. However, there is an exception. If you see TCP options, it is again sort of TLV based. So I highly recommend you to watch this episode so that you will understand. If I discuss, even I have discussed, as you can see, the last episode or in somewhere in the middle, I have even discussed this episode about protocol fixed header, manual parsing and packet generation and stuff like that with some examples. So I suggest you to watch the same. So that is what I did this slide. So before even discussing this slide, let us just have a look of the code so that you can understand what is this all about. So here is my simple code which I came up with. This is based on my old sample UDP socket code, which you can go here, tutorials, and you can explore. You can find one of the articles I just posted the same. So this is based on this code. So I took the code and then I have added the same. In fact, I gave this as an exercise for one of my students. Soon after he joined, he was requesting me to teach the same. So this is something I gave this as an exercise, then he was doing his changes, and then I was explaining again some more basics. So this is based on the code. So effectively what we are doing is we are taking a UDP socket code, so that you can generate a custom protocol. You can send it from client to server, and then server can parse the same. It's an application layer protocol. You can do it in kernel space, you can do it in application layer, whichever way you want. So the focus is not about socket code. This is some misconception. Anyone starts learning about network software programming, they start with some stupid socket programming in TCP, UDP and all this stuff. So come out of that misconception. You don't need to focus much on socket code. Socket code is just you can facilitate to send any data from one end to other end. You can choose whether it is UDP or TCP, whichever way you want. That's about it. So it is effectively your kernel does that, and it's what facilitates as a platform, so that in user space you can send data to and fro via socket code. If you do it in kernel space, you can create your custom skbuf data structure instances or packets in the skbuf data structure, and then you can send it directly via device driver. So that's all about. So don't focus much on socket code. Let's focus on the protocol creation, how it can be created, how it can be defined, and then how it can be parsed. So switching back to my slides, you can see here this is one of the slide. If you see, what I did is this sort of explains the design or standard, and then the sequence what I'm trying to put in this episode as a part of example. So we are taking a simple like a math protocol I did. So all I need is if you send two values in 2 bytes, I mean 1 byte for each value. Let's not complicate, let's make a very simple protocol in application layer so that we can understand how we can define it, and this is how RFCs are written. So you have this standard, we can take a protocol, a fixed header protocol, always it should contain 3 headers, unlike something you take a IP header. So if you go here, IP header, if you see here images, so a typical Ipv4 header looks somewhat like this. So it is like, since they cannot put all the bytes one after another, or all the fields one after another, they made it in the groups of 4 bytes. Whereas in our example, we can take, this is the fixed protocol header. In the protocol header, we have 3 fields. First byte is an operator which contains plus, minus, equal, whatever it is. The second byte, it contains one value in 1 byte. The third byte is going to be the second value in 1 byte. So this is what effectively we are putting in a UDP packet, and we are sending from client to server. The server is going to get this buffer, and then the raw bytes. It is going to parse that into a data structure, and it is going to send a reply after it computes value 1 and value 2, and its result it is going to send as the first byte is going to have that equal sign as a result, and then it is going to send the result in the first byte of that reply. So we can ignore the second byte. As I say, this is not about how do you do mathematics, this is about how do you design a protocol. So let's focus on that. So it is going to send, after it does all this logic, it is going to send that to the UDP client. So this is what effectively we are trying to do. So for doing this, we need to do certain definition of a protocol in the form of a data structure, and then we need to write some APIs so that in both client and server it can use these APIs and it can use this data structure. So if you hop onto the code, you can come here. As I said, just ignore all this socket programming crap. So let's focus on the protocol part. So once you come here, you have this data structure which I have done. I'm naming it as a math_proto. So we have this instance empty. So in the empty we are populating just as you've seen in this slide. So if you go here, you see here the first byte I'm populating as a value plus. The second byte is going to have some value like 0a, which is nothing but in decimal it is 10. The second byte or the third byte or the second value is going to have the value as 1. So effectively we are adding 10 plus 1 and we are saying it's an operation as plus. So that's what we are doing here. And then this API, it just dumps it like a debug of that data structure. So anytime if you design a data structure and if you write APIs, I highly recommend you to write some debug APIs so that you can debug that API whatever you have written. You don't need any complicated GDB and all this crap to debug your code. So whether you do in kernel space, whether you do in user space, try having a habit of writing such APIs so that it helps you to debug from the time you start writing your custom data structures and APIs. So once it is printed, as you can see, this is just an optional step. You can even comment, it doesn't matter. So after it is done, we are doing a math proto create packet so that it takes this data structure, that MP data structure instance, and then it creates or populates that buffer. So effectively, if you see the socket code, you are going to send packet bytes. Even you do in kernel space something, it is going to send the packet bytes. So we are converting the data structure, or we are getting the data structure and we are putting in a packet bytes format, so that with that you can do a send to message and we can send from the client to server, and with that the job is done. And whatever it is received, you can see here, once it reaches the server is going to reply, and whatever it receives, we are just taking that and we are doing a demo dump here. It's just a raw byte dump of whatever received buffer, and then we are parsing the same. Before parsing, I am checking if its length is 3, and then I am using another API math protocol parse packet, and I am getting this MP populated from this raw buffer. So once it is populated, again we are doing a demo print debug API call. With that we get whatever server sends, we can display in the UDP client as well. So let us just hop on to this header file. It's a common header file, both I wrote so that server and client both can include, and it is what contains this struct and this all APIs. So if you see here, this header file is also included in the UDP server as well as UDP client. So this is the header file. So it's very simple. Again, our focus is not about what it does in terms of mathematical operation and its precision, whether it is added and then put in 2 bytes, all this bullshit. Let's focus on how do you define an RFC and how do you architect a protocol. So let's focus on that. And so with that, if you see here, with that context, if you see here, this is our data structure, what I designed. So you can see it is fairly simple. As you must have seen many times, I have a habit of writing just one line of code. So it kind of makes it easy whenever it is a quite obvious code. So I feel this is quite obvious, and this sort of mimics my architectural context, what I defined here. So you have 3 bytes. So you have a struct with 3 unsigned chars. So you have that first one is an operator, second one is value, and the third one is a value. So you have 2 values and an operator. So this is the standard of this math protocol. So with that we have all this APIs. So one API is all about to do parsing. Whenever it receives that raw buffer, it has to populate in the data structure. So we have this parser API. So you can do 2 types of parsing. You can do raw manual parsing. You can also do raw automated memcopy type of, or else you can do some typecasting, you can do memcopy or anything like that. So you can do that way, you can do this way. So both the ways you can do. it. So you can do that way, you can do this way. So both the ways you can do. I'm not sure whether it is this one is I have tested because I just wrote the code, but this is something which I used. So you can do this. You can see here it is getting this pointer of MP, and it is getting this buffer. So since we are supposed to parse the buffer into the data structure, you can see here it is just doing a very simple manual parsing. The first byte it is assigning to this operator, second byte to this value 1, third byte to this value 2, as simple as that. So with this the parsing is done. So as I said, you can do even this way, which effectively going to work. So because you are just doing a mem copy of buff to that MP, and all of these are just 1 byte value, so you don't have to do any network to host length or such APIs, or host network network short to host I mean to say these APIs, I forgot, I'm sorry, man n to hs, yeah, this series of APIs. So some you need it for 32 bytes, some you need it for 2 bytes. So you don't need to do any such conversion. So this is the reason I'm just keeping this code very simple. So we don't need to do any such APIs. We can do directly a mem copy. It is going to work. And the other API is so you can use, of course, you can use either of the variants. One is parse packet, the other one is parse packet 2. The packet 2 is the automated one, the other one is the manual one. So coming down, you can see to send the packet, you need this creation API. This is something is extensively I have discussed in this video series. So it is, as I said, it is quite long back I did it, these video series. So I have done it in the whiteboard explaining the same. So you can refer. So you can see you have this create packet API. It is again simple. What we are doing is we are having the data structure populated. From the data structure you need to create that raw bytes. So this is one way to do. You can even do some kind of mem copy as well. So I want to avoid mem copy because it can create any issues. If it is something like big endian, little endian, you need to do all those things. So let's stick to simple architecture so that you can understand the actual basics of how you can define a simple protocol and write APIs, and then how you can put everything together. So if you see here, it's fairly straightforward. You can see the first struct member variable I'm assigning to byte 0, the second one to byte 1, the third one to byte 2, as simple as that. So with this the buffer is created. So this is what this API does. And the other API is this debug API. You can see here I'm just populating whatever it is, having values MP of operator and value 1, value 2. I'm just displaying it in that 0 to x in 2 bytes form, so that we can get that raw hexadecimal contents, whatever it contains. So this is what it is being done. And here is our actual calculate API. So this API, you can see here, it is taking this data structure and it is computing its values with whatever operator you have passed, and it is storing the result in this MP2. So that's what is happening. You can see here, if it is plus, it is doing a plus, if it is minus, it is doing a minus. So as simple as that. Let's not get into unsigned and signed and all this complications. As I said, let's focus on protocol development. Let's ignore the mathematical part of that. So it does the same. It stores the result here. The result is also 1 byte, and with that we are populating this MP2 data structure. So the MP2 operator is equal to, and its value 1 contains the result, the value 2 is not applicable, or you can just ignore the same. So only one value is considered whenever it contains the equal to symbol. So that's what I have mentioned in this picture. So you can see here, now it is very clear. You have this UDP packet, you are sending a query from UDP client to the server, populating what is the operation and what is the value and what is the other value. So these two values it will take and it will do that operation in the UDP server, and it is going to send the reply. So the reply will contain equal to, and the first byte is going to have the result, the second byte is not applicable, or you can ignore the same. So the UDP client receives the same, it parses it, and it just does a debug print on the screen. So with that we can get to UDP server source as well. So you can see here again it is fairly simple. You have all this socket code here, and below that once you receive the bytes, we are checking that and we are doing a manual print a dump of the same, so that whatever we have received the bytes, we are displaying a raw dump of that. Okay, and below that is our actual parsing starts. So you can see here I am checking if the length is 3, and then because as per our standard it's a fixed header, it should always have 3 bytes. So I am checking if its length is 3, and I am using this data structure. So I'm creating 2 instances. One is the MP and the other one is MP_result. So initially it is doing a parse, so I'm passing this pointer of MP and then that buff whatever we received. So with that the MP is populated. So the MP is populated. So once it is populated, I'm doing a print debug of the same, so that we will come to know whether it is being parsed properly. So next after that I'm doing a calculate. So with that it calculates the same and it populates the result in the MP_result. So once it is done, we are doing again a print debug of that data structure instance. So once everything is done, we are creating a packet to send this reply from the UDP server to the UDP client. So this is what it is. So since the result is stored in MP_result, we are passing this pointer instance. So with this it is done. So we are just sending it back to the UDP client. So that's what you have seen just before. So it is receiving from server to the UDP client. Once again it is checking the raw bytes, and then it is just doing a parse, and then again it is doing that print debug. So this is what has been illustrated in this diagram. So if you go to the next slide, you can see here, as I said, you have this fixed size header. So in this case it's a very simple fixed size header, versus this is not any TLV. So this TLV is extensively used in user space application layer protocols. So best examples include even SSL as well as HTTP as well as DNS and things like that. So any such application layer protocols, usually they are TLV based, because you can have any amount of length. If you need to send any database rows and fields inside the database, you can create a TLV based protocol structure, so that you can have any length of this values you can share. So we are not using this architecture, so that we can make this parser simple. If you start using TLV based, it's extremely difficult to do in C code, and it is quite easy to do something in a scripting language. So let us avoid using some TLV based stuff. Let us stick to the basics. So this is how you architect a simple protocol, and you define an RFC. An RFC definition is nothing but, a protocol RFC definition is nothing but you set some standards and you define what exactly each byte contains, and what are its rules, and what are its a malformatted packet it defines. So in case if suddenly it receives 3 bytes, then it's a malformatted or it's not a valid packet. And in case if it receives some other operator which is not defined here, that also is considered as a malformatted packet. So you can also write some rules here which I have not written. So before even parsing, you can check certain criteria, and then you can say a parse error in case if it doesn't matches that criteria, which I'm not doing it here. I'm just doing a very dumb parsing. Instead you can just do if buff of 0 is not equal to you can tell plus. Okay, you can define all these rules. So and you can tell minus, and it is not equal to equal, and you can return some error. So you can do something like this, else you can just accept this. So you can do any such combination. So this actually defines the actual way of doing a protocol, so which I'm not doing it. Of course you can define all these rules as a part of the protocol standard. So let me take this out, and if you go to the terminal, you can see this is the code. I'm just going to share this code so that you can download it and you can use it. You can execute at your end, and then you can write your own add-ons on top of it in case if you're curious. So this is my compile script. Usually I'm not a fan of make files and all this garbage, so I generally write compile scripts like this. So take this compile script, so you can just compile it via this. So this compiles the code, you can see here, and it generates a UDP socket v2 client and server binaries. So we can run UDP server so that it registers a UDP port, and then it listens to that port, which is the port is 6810, and then we can run the UDP client. So in this case, I have just hard coded the value 1 and value 2. You can just do a scanf, you can do any such combination. So I'm not interested about, as I said, I'm not interested about the actual mathematics it does, whether it is doing it right or not. I'm more interested about the protocol part. So after executing, you can see it's a dump. So you can see here UDP client v2, and we have this operator which is 2b, which is the ASCII value for plus, and then we have these two values which is a and 1. So a and 1, a is 10 in decimal and 1 is 1, so it is sent to the server, UDP server, and once it got this packet, you can see here it is telling it has received 3 bytes, and this is the raw dump of that buffer even before parsing, and then it has parsed the same. You can see the MP contains this 2B, 0A and 01, and then the result is 3D, which is maybe the equal to symbol of the ASCII value, and then its value is 0B because A plus 1 is B in hexadecimal. So that's what it has got in MP underscore result. So you can see here, and it's sent to UDP client. You can see here 3D 0B00. So with this, it's confirmed and it is working. You can see here, this is the raw dump of that bytes, whatever it received from UDP server to the UDP client. So we can even do one more thing. We can go here and we can sudo Wireshark. So we can capture the same in Wireshark so that we can analyze it is all working fine. So this is some habit you need to pick. Don't use TCP dump or something. Just use Wireshark so that you get that proper way to investigate what is happening in your network. So always use Wireshark whenever you design or architect any protocols of your own, or you need to investigate any issues in network activity. Generally use Wireshark. So let us do one more iteration, and let us capture the same. I think I have turned off the server, you can see here, so it is waiting. So let me turn on the server and let me cancel this and let me just run it once again. So with that, you can see here, let me stop this operation. So you can see here, earlier it has sent this packet with this 3 bytes, so 2B, 0A, 01, but since the server is not turned on, it has got that destination not reachable or unreachable ICMP reply packet, and once the server is turned on, you can see here it sent this packet from client to the destination port 6810, the port which server is registered, and it is listening. So you can see here it sent this reply. It contains again these 3 bytes, which is 3DBB00. You can see it's ASCII representation of the first byte. The second ones are binary data, so it is not showing it. It is showing non-printable characters as dot. As you can see in Wireshark, it shows the same, or any hex editor. Okay. So the 3D it is rendered as equal to, whereas in this case the first byte 2B is rendered as plus in Wireshark. So this is how you architect a protocol, and as I said, I'm going to share this code so that in the video description you can go from there to Linux channel website. Obviously I'm going to link from there to Linux channel website. In the Linux channel website below you can see the references, as well as you can find the download link of this code, so that you can download and you can also experiment. You can also add anything of your wish, and then you can learn further. You can even do as a challenge, you can even do this values into 2 bytes instead of single bytes, and then you can do that network to host short or such APIs you can use, so that you can convert that buffer format into a unsigned short format, means 2 bytes unsigned short value. So you can do any such combination. You can even do into 4 bytes values. You can add some more additional bytes to this protocol, or even you can make it into a sort of dynamic fixed header protocol, so that if I pass plus and then some 5 bytes, it is going to add all the values of this 5 bytes, means 4 values plus the operator, and then it is going to send the result from UDP server to the UDP client. So you can do any such combination, and this is what is the basis of designing a protocol. So any protocol will contain components like this. So it will contain a data structure, it will contain a parser. Of course it will also contain certain APIs to check whether it's a valid packet or not. So I need to do such API here, and even that API you can call it inside rather than doing directly inside. As I said, you can check if it is operator is not registered, you can send a error or something like that, or else in the server it can just show any error, and then it can stop doing further operation, or else it can send some kind of error code back to UDP client. Instead of sending equal to, it can send some kind of error code instead of sending that reply. So that defines the server received a wrong packet, and this is a sort of malformated protocol packet, so that it is sending an error reply to the UDP client, so that UDP client knows, and then it can recover or it can do further operation. So you can do all sorts of combination. Any full-fledged properly implemented protocol will contain all these components. So that's what it is. Although as a demo I have not implemented, it is good that you have further some more APIs, and all these APIs constitutes a proper implementation of a network protocol. So you can make such APIs as a private APIs, static, you can define as a private API, so that you can call such APIs over here, and then you can parse it. So any protocol will contain, or a protocol stack will contain, a data structure and a few APIs, especially APIs to parse and then build packets and then do certain other operation, and of course any FSM. So in this protocol, since it is very simple, it doesn't have any FSM. FSM stands for finite state machine, so it doesn't have any FSM. All you can tell an FSM equivalent is this two if else statement. So FSM is what especially does any packet it receives, what to do with that packet. The finite state machine defines what to do with such a packet. So you can consider for this type of protocol, since it's a math protocol, the FSM is all about doing some calculation, so that it gets this data structure which is populated, and then it can take some action. Versus if you check TCP, you can see TCP finite state machine. For TCP, the FSM is somewhat like this. So this is the FSM for TCP. Whereas in our case, since it's a very simple protocol, we don't have any such complicated states and other stuff. There is no state at all, first of all. So this is a very simple query reply. It's more like a DNS rather than any complicated protocol, because DNS works like that. It doesn't have much of any state. You send a request, DNS request, it's going to send a DNS reply. And same thing even with ARP protocol as well. You do a ARP request, it sends a ARP reply, as simple as that. So whereas in this case, as you can see here, in the case of TCP, it has various states, because it establishes a connection, and then the connection is going to exist for some time, and as long as the connection is existing, it is going to send some keep alive messages and all those activity behind the scenes. The kernel does that although your TCP socket code doesn't do it consciously, the kernel does that subconsciously without your notice. In case if you are just doing it as a socket code, the kernel does that. But user space, as you use a TCP stack, you don't need to bother about whether it maintains a state or not, because it's something kernel does that. So in the end, if you think of any protocol, it is going to constitute all these components. You have the network RFCs or the protocol RFCs, which defines the overall objective of the protocol and how the protocol is architected and what are its do's and don'ts. And as a reference, you take this RFC and do a network stack. You can do a network stack in C, you can do in C++, you can do in any language or any scripting language, or you can do in Windows, you can do for Linux system, or you can do in user space, or you can do in kernel space. It doesn't matter. Any network stack is going to have all these components. But having said that, it again depends on protocol to protocol. Some components may exist, some components may not exist. As I said in my example, you don't need any extensive FSMs. Whereas if you see a real protocol, a real implementation, often it may have some kind of FSM or some kind of a state if it maintains a state. If it doesn't maintain a state, still you may have many static APIs, internal APIs, so that it checks the validity of the protocol. It checks, it may have inside the protocol, it may have any checksums. It can check if the protocol is malformatted, if the protocol header is malformatted or something, it can do all sorts of checks even before parsing it further, so that it gets populated into a data structure. So all these things comes into the picture. So hope this gives that real big picture and the full scope, so that it really gets you to start designing or understanding, architecting your own network protocols from this, and as well as it makes you easier to understand any existing protocols. I have seen often once they watch my UDP header, TCP header, all these video episodes, sometimes they do binge watching and then they send this mail asking me to do a complete video episode on some kind of live demo of showing the same. So hope you guys loved watching this episode. If you have any questions, if you have anything to discuss, be in touch via mail. Thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.